At 10 to the power of 100 years, the universe's largest black holes, the supermassive remnants at the centers of merged galaxy clusters, will complete their Hawking evaporation. The last of them will emit its final burst, leaving behind the most diffuse and thermally featureless physical environment that can exist under known laws of physics. Photons redshifting toward zero energy, electrons and positrons separated by distances larger than the current observable universe, neutrinos drifting on trajectories they have followed for times literally incomprehensible in any unit of measurement connected to human experience. Temperature asymptotically approaching absolute zero without reaching it. Entropy at its maximum possible value. The universe as near to heat death as any physical process can bring it. After this, in a cosmological sense, there is no after. Not because time stops. Time does not stop. The universe continues to expand. Photons continue to redshift. But nothing happens. No temperature difference exists to drive a thermodynamic process. No concentration of mass exists to drive a gravitational process. No quantum state transition has enough energy above the background to be distinguishable from thermal noise. The universe exists in a state of maximum entropy and minimum information, unless the vacuum is unstable, in which case, at some point on a timescale that could be as short as the current age of the universe, or as long as numbers that exceed by many orders of magnitude, even the black hole evaporation timescale, a quantum tunneling event nucleates a bubble of true vacuum. The bubble expands at light speed. The laws of physics within the bubble are different from the laws outside. What the bubble contains, what processes occur within it, what structures, if any, can form under its different physical rules is unknown because we do not know the true ground state of the quantum vacuum or what physics it supports. This is the deepest uncertainty in cosmic eschatology. Not the timescale, not the sequence of stages, not the specifics of Hawking evaporation or proton decay. The deepest uncertainty is whether the current laws of physics, the rules that have governed every process since the Big Bang, are permanent features of reality or temporary conditions of a metastable vacuum whose final state has not yet been reached. If they are permanent, the universe approaches heat death asymptotically, and the question of what happens after is meaningless in the physical sense. If they are not permanent, the universe undergoes a phase transition to a new ground state at some point, and the nature of that new state is not just unknown, but unknowable from within the current vacuum. The physics of the true vacuum cannot be predicted from the physics of the false one by any method available to observers living in the false vacuum. The universe may have a second chapter whose rules we cannot read, or it may have only one chapter, very long, ending in a silence too deep to disturb. Current physics cannot distinguish between these possibilities. The experiments being done now, measuring the Higgs boson mass and the top quark mass with ever greater precision, are measuring the stability of our chapter. They will tell us whether our laws of physics are the last word or only the first. That is the frontier, not a distant one, not a merely theoretical one, but an active experimental frontier, where the question being asked is whether the universe we can observe and measure is stable on timescales longer than anything we have so far contemplated. The answer is being written in data right now, in particle physics laboratories, in telescopes measuring the expansion history of the universe, in underground detectors waiting for a proton to decay. the universe does not end on a schedule. It ends when physics dictates, and physics is still being read. The numbers that define the end. There is value in sitting with the actual timescales of cosmic eschatology, because the numbers themselves convey something that prose descriptions cannot fully capture. The universe does not have one ending. It has a sequence of endings, each separated from the previous by intervals so large that human intuitions about time dissolve completely. What follows is a timeline, not in years as we ordinarily use that word, but in orders of magnitude, each step representing a leap not by addition, but by multiplication. Right now, we are at approximately 10 to the power of 10 years since the Big Bang, 14 billion years, give or take. In this era, roughly 200 billion trillion stars are burning across the observable universe. Galaxies are forming, merging, and dispersing. The cosmic web is still being built by the slow accumulation of matter along filaments. This is the stelliferous epoch at its height, or slightly past its height, since the peak rate of star formation was roughly 10 billion years ago, and has been declining ever since. At 10 to the power of 11 years, 100 billion years from now, the Milky Way and Andromeda will have completed their merger billions of years earlier, having collided in roughly 4.5 billion years, and undergone multiple passes before settling into the large elliptical galaxy, sometimes called Milkomeda. The local group will be gravitationally bound and isolated, every other galaxy cluster, having receded beyond the cosmological event horizon driven outward by dark energy, faster than any signal or traveler could follow. The universe beyond the local group will be unreachable and soon invisible, as the last photons from those departing galaxies redshift beyond any detectable frequency. At 10 to the power of 12 years, 1 trillion years from now, the last sun-like stars will have exhausted their fuel and become white dwarfs. The only active fusion will be occurring in the smallest red dwarfs, burning so slowly and so completely that they will persist for another order of magnitude or two. The universe will be dim, lit only by these dull red embers. Any civilization that has survived to this epoch will have adapted its energy sources accordingly, no longer dependent on the brilliant yellow and blue stars of the current era, but living by the faint warmth of the last stellar furnaces. At 10 to the power of 14 years, 100 trillion years from now, the last red dwarf will have burned out. No new stars are forming. The gas reservoirs from which stars could form have been consumed or dispersed. The stellar era of the universe's history is over. Every stellar remnant has already cooled substantially. White dwarfs are now very faint. Neutron stars have been dark for trillions of years. Black holes persist, fed by the occasional infall of cold matter that drifts into their gravitational reach, but growing only imperceptibly in the near emptiness of the post-stellar universe. At 10 to the power of 37 to 10 to the power of 40 years, if proton decay occurs at a rate consistent with current theoretical expectations, all of the ordinary baryonic matter in the universe will have dissolved. The white dwarfs that were cooling through the previous epochs will have eroded from within, their constituent protons decaying one by one into lighter particles. Neutron stars will have undergone similar dissolution. The stone, cold remnants of stellar evolution will cease to exist as organized matter. What remains is a universe of black holes, photons, neutrinos, and the lightest stable particles, drifting through space at separations that have grown unimaginable over the preceding decillions of years. At 10 to the power of 67 years, the smallest stellar mass black holes will be approaching the end of their Hawking evaporation. A black hole of a few solar masses, which has been losing mass through Hawking radiation for an almost inconceivable span of time, will begin its final accelerating evaporation, its temperature rising as its mass decreases, culminating in a brief burst of high-energy radiation as the last of its mass converts to photons. This flash is the death of a black hole that was born in a supernova explosion during the first billion years of the universe's history, an object that has outlasted every star, every galaxy, every complex structure that has ever existed, ending in a final pulse of light that will travel outward through a universe so vast and so empty that it will never encounter another particle before its energy is diluted to nothing by the expansion of space. What we know, what we infer, and what may lie beyond our models. Let us take stock of where we actually stand, not in the sense of which scenario is most likely to be correct, but in the sense of which parts of this account rest on confirmed physics, and which parts rest on extrapolation, inference, or theoretical frameworks that have not yet been observationally tested. The second law of thermodynamics is confirmed. Entropy increases in all observed systems. The heat death of isolated systems is a consequence of this law applied without time limit, and represents the endpoint most consistent with confirmed physics extrapolated to cosmic scales. The stelliferous era, the age of stars, is confirmed to be finite. Stars consume fuel. The rate of new star formation is declining. The last stars will burn out. This is not speculation. It is the physics of nuclear burning applied to the observed distribution of stellar masses and the observed rate of star formation across cosmic time. Hawking radiation is theoretically robust, but not directly observationally confirmed for astrophysical black holes. The argument combining quantum mechanics and general relativity is compelling. It has been confirmed in analog systems, experimental setups using sound waves in supersonic fluid flows that simulate the mathematics of black hole event horizons, and the thermal spectrum of radiation from these analog black holes matches Hawking's prediction. But no one has directly detected Hawking radiation from an actual black hole. The evaporation of black holes over googles of years is a firm prediction of the combination of quantum mechanics and general relativity, but rests on an extrapolation of that combination into a regime where neither theory has been tested. Proton decay is predicted by grand unified theories, but has not been observed. Current experiments have ruled out the simplest GUT predictions, but more sophisticated models allow proton lifetimes that remain beyond current experimental reach. Whether protons decay at all is a genuinely open empirical question. If they do not, the matter in white dwarfs and neutron stars will not dissolve through proton decay. These objects would eventually find other endpoints, possibly through quantum tunneling processes that operate on even longer timescales, but the timeline would differ significantly from the proton decay scenario. Vacuum stability depends on the precise values of the Higgs boson mass and the top quark mass at a level of precision not yet achieved. Current measurements suggest metastability or marginal stability. Future measurements will sharpen this. But even if the vacuum is metastable, the decay rate is so slow that vacuum decay is not expected to be the first thing that happens to the universe on cosmological timescales. It remains a possible fate on timescales longer than any other process we have discussed. Dark energy's nature remains unknown. The equation of state W has been measured to be consistent with -1, but deviations that would lead to the Big Rip are not ruled out. Current and near-future surveys will tighten the measurement of W substantially, potentially determining whether the Big Rip is a realistic scenario within the next decade of observational cosmology. Cyclic models, whether ekpyrotic or conformal, are theoretical proposals with specific observational predictions that have not yet been definitively confirmed or ruled out. The detection or non-detection of primordial gravitational waves at cosmological amplitudes will be a decisive test of the ekpyrotic scenario. The status of Penrose's Hawking points in the CMB data is actively disputed. What this survey of confirmed, inferred, and speculative physics reveals is a picture that is both more complete and more uncertain than popular accounts typically convey. We have strong reasons to believe the universe will end its stelliferous era. We have strong theoretical arguments, though not direct observation, that black holes evaporate. We have open empirical questions about proton stability and vacuum stability that will be settled by experiments within the coming decades. We have complete uncertainty about whether dark energy will maintain its current properties or evolve in ways that change the ultimate cosmic fate dramatically. The universe is not keeping its eventual fate a secret. It is writing that fate in the values of physical constants and the equation of state of dark energy and the lifetime of the proton, values that experiments are measuring with increasing precision. The story of what happens at the end of cosmic time is being written in physics laboratories today, in supernova surveys cataloging the universe's expansion history, in underground detectors waiting for a proton to disintegrate, in precision measurements of particle masses at accelerators. The ending of the universe is a physics problem, and like most physics problems, it is yielding to measurement and inference. The universe began in conditions of extreme order and low entropy. Everything since has been the slow diffusion of that initial order, the gradual unfolding of available energy gradients through nuclear burning, gravitational collapse, and thermodynamic processes operating at every scale. The heat death is the asymptotic endpoint of that diffusion, the state toward which every process has been heading since the first microsecond of existence. It is not a catastrophe. It is a completion. The universe running all the way to the bottom of the thermodynamic slope. It has been descending since the Big Bang. What lies at the very bottom, whether a permanent equilibrium, a vacuum transition, a cyclic rebirth, or something that current physics cannot describe, is the deepest open question in cosmology. Every observation sharpening the measurement of W, every experiment constraining proton lifetime, every theoretical advance in quantum gravity narrows the range of possible answers. The universe's ending is unknown. It is not unknowable. And the physics being done right now to determine it is among the most consequential scientific work of our era. You are alive in the stelliferous epoch, the most information-rich, the most energetically vibrant, the most thermodynamically structured period of cosmic history that has existed or will exist. The stars burning in the sky above you are the primary mechanism by which the universe's initial low entropy is being converted to high entropy. You are, in the most literal sense, witnessing the peak of the process. The entropy gradient that makes your life possible. The sunlight that drives the biosphere. The nuclear processes that power the physics you use to study the universe. All of it is the early bright chapter of a story whose later pages are written in cooling and darkness and silence. the universe will end. Not today, not in any timescale meaningful to any living thing, but eventually in ways that physics already understands at least partially, and is working to understand more completely. What it means for the universe to end, what ends and what, if anything, persists, whether endings are final or transitional. These are not merely scientific questions. They are the deepest questions about the nature of existence, stated in the language of thermodynamics and quantum mechanics and dark energy, and the stability of the vacuum. We have the language. We are learning the grammar. The last word of the universe, whatever it turns out to be, is still being composed. The observer problem and what ending even means. We have been tracing the physical evolution of the universe through stages defined by specific processes: stellar burning, stellar remnant cooling, proton decay, Hawking evaporation, and possible transitions to new states through vacuum decay or cyclic mechanisms. But there is a question running underneath all of this that deserves to be stated explicitly. What does it mean for the universe to end from the perspective of an observer embedded in it? The heat death scenario does not kill observers in a single moment. It creates conditions progressively less hospitable to the existence of complex, organized matter. Life, as far as we know it, requires energy gradients, temperature differences that can drive chemical and thermodynamic processes. The energy that powers life on Earth ultimately comes from the temperature difference between the Sun's surface at about 5,800 Kelvin and the cold of space at 2.725 Kelvin. Life is an entropy-generating process that captures some of the energy flowing from hot to cold and uses it to maintain and reproduce complex structures before that energy continues its path to equilibrium. As the universe cools and stars burn out, the temperature differences available to drive life-sustaining processes diminish. The last red dwarfs, burning for trillions of years, provide smaller but real energy gradients. Civilizations with sufficient technological sophistication might exploit the gradients available from stellar remnants, from the tidal heating of moons around brown dwarfs, from the evaporation of black holes. Freeman Dyson, in a remarkable 1979 paper, analyzed the physics of life in an ever-expanding cooling universe and argued that an information processing system could in principle survive indefinitely by slowing its metabolism in proportion to the available energy, processing fewer and fewer bits per unit time, but never stopping completely. Whether this constitutes survival in any meaningful sense, or whether survival of a nearly infinitely slowed information processor is distinguishable from ending, is as much a philosophical question as a physical one. The question becomes more pointed with Boltzmann brain considerations. If the universe persists indefinitely at near maximum entropy, the thermal fluctuations that randomly assemble complex structures will eventually, in a cosmos with infinite time remaining, produce observers of all types and at all scales. The vast majority of the universe's history would then be dominated by Boltzmann brain observers rather than by observers that evolved within structured cosmic epochs. If you are reading this, you are almost certainly an ordinary observer in the stelliferous era, a state that exists for a fleeting cosmological moment relative to the near-infinite heat-death era. The probability of being an ordinary stelliferous era observer relative to a Boltzmann brain observer depends on how long each epoch lasts and how many observers each epoch contains. In a universe that persists for infinite time after heat death, Boltzmann brains win the numbers game by an infinite margin. The standard response is that ordinary observers in structured cosmic epochs are far more likely to have accurate memories and reliable observations than Boltzmann brains, whose fluctuation-assembled memories are almost certainly false. Any cosmological reasoning should therefore preferentially trust observations that are consistent with being an ordinary observer rather than a fluctuation. But this response has the uncomfortable structure of assuming the conclusion. If you have not independently established that you are an ordinary observer, you cannot use the reliability of ordinary observation as evidence that you are one. The Boltzmann brain problem is one reason why some cosmologists argue that the universe must have a definite end, rather than an infinite future equilibrium. A universe that ends through vacuum decay, through the Big Rip, or through some other finite time mechanism avoids the infinite accumulation of Boltzmann brains. Any model of cosmic eschatology that leaves an infinite future of near equilibrium state is arguably self-undermining as a theory about what observers should expect to find themselves observing: the cyclic universe, and the question of whether this is the first time. Against the backdrop of heat, death, vacuum decay, and the Big Rip, there's a class of cosmological models that takes a different approach to the question of cosmic endings. Rather than accepting that the current universe represents the whole story, these models embed our universe in a larger cycle, a sequence of expansions and contractions in which what looks like an ending is actually a transition to a new beginning. The most developed modern cyclic model is the ekpyrotic cyclic scenario, proposed by Paul Steinhardt and Neil Turok in the early 2000s and refined extensively since. In this model, our universe exists on a three-dimensional membrane called a brane, embedded in a higher dimensional space. A second brane exists parallel to ours, separated by a small distance in the extra dimension. The two branes are attracted to each other by an interbrane potential, and when they collide, the kinetic energy of the collision is converted into the hot, dense plasma we identify as the Big Bang. After the collision, the branes separate, and the universe on each brane expands and cools in a pattern resembling standard cosmological history. Eventually, the branes slow, stop, and are drawn back together by the interbrane potential, leading to another collision, another Big Bang, another cycle. In the ekpyrotic cyclic model, the Big Bang is not a unique creation event. It is one episode in an eternal sequence of collisions. The universe before our Big Bang was not nothing. It was the preceding expansion phase of the same cyclic sequence, a cosmos that expanded, cooled, and ultimately contracted back to the collision point that seeded our current expansion. The question, what came before the Big Bang, has a specific answer in this framework: a previous ekpyrotic cycle, with its own stars and galaxies and presumably its own history of complexity, now inaccessible because the collision that produced our universe destroyed or reset the information that described it. The cyclic model makes specific observational predictions that distinguish it from standard inflationary cosmology. In particular, it predicts a negligible amplitude of primordial gravitational waves, the tensor perturbations that inflation generically produces, and that next-generation cosmic microwave background experiments are searching for. Detection of primordial gravitational waves at the amplitude predicted by standard inflation would severely constrain the cyclic scenario. Non-detection would be consistent with it. Current upper limits on the tensor-to-scalar ratio from the Planck satellite combined with bicep/Kekere data, already rule out the simplest inflationary models and are consistent with the cyclic prediction of very low tensor amplitude. Experiments over the next decade will sharpen this test significantly. Conformal cyclic cosmology, proposed by Roger Penrose, offers a different mechanism for a cyclical universe. Penrose argues that the very distant future of our universe, after all, black holes have evaporated, and all massive particles have either annihilated or become so energetically cold that their rest mass is effectively irrelevant, will be conformally equivalent to the beginning of a new Big Bang. The mathematics of conformal geometry allows a rescaling of space-time that maps the infinite cold future of one cosmic aeon onto the hot, dense beginning of the next. The universe does not contract and re-expand. It undergoes a mathematical transformation that connects the endpoint of one epoch to the starting point of another. Penrose's model makes a striking prediction. The collision of supermassive black holes in the previous aeon would produce pulses of gravitational radiation that would imprint circular temperature patterns on the cosmic microwave background of the subsequent aeon. These Hawking points, as Penrose calls them, should appear as concentric rings of anomalous temperature in the CMB. Penrose and colleagues have claimed to find evidence for such patterns in the Planck data. The interpretation has been challenged vigorously by other researchers, and no consensus has emerged. Whether the claimed rings are genuine features of the CMB or statistical artifacts in a complex dataset remains actively debated. Both the ekpyrotic and conformal cyclic models share a common philosophical impulse. They refuse to accept that the current universe is a first and final instance, that what we observe is the only episode in a cosmos that began in absolute nothingness and ends in absolute equilibrium. Both models embed our universe in a larger temporal context, whether a sequence of brain collisions or a mathematical transformation connecting aeons that gives cosmic history a structure beyond the single arc from Big Bang to heat death. Whether either is correct, physics does not currently know. Both make predictions that future observations can test. Both are mathematically serious. Both represent genuine cosmological alternatives to the standard picture of a universe, with a unique beginning and an eventual final state. The universe's past and future may be far longer and far stranger than the single episode we can observe. The Big Rip and what dark energy might do. Everything discussed so far has assumed that dark energy behaves as a cosmological constant, an intrinsic energy density of space that remains fixed as the universe expands. This assumption is consistent with current observations but not proven. The equation of state parameter of dark energy, which physicists call W, and which for a cosmological constant equals precisely -1, has been measured to be consistent with -1 to within current observational precision. But the precision is limited. A value of W slightly different from -1 would have profound consequences for the universe's long-term future. If W is less than -1, meaning dark energy is even more negative pressure than a cosmological constant, the expansion of the universe does not simply accelerate at a fixed rate. It accelerates at an increasing rate. The scale factor of the universe, which describes how much space has expanded relative to a reference epoch, does not just grow, but grows without bound in a finite time. This divergence in a finite time is called the Big Rip. It was first systematically analyzed by Robert Caldwell, Mark Kamienkowski, and Nevin Weinberg in 2003, and the name captures the physics accurately. Dark energy with W's less than -1, called phantom dark energy, becomes increasingly dominant as the universe expands because its energy density grows rather than remaining constant. Eventually, it becomes strong enough to overcome every other force, from gravity holding galaxy clusters together to electromagnetism holding atoms together, to the strong nuclear force holding protons and neutrons together in nuclei. The timeline for the Big Rip, if phantom dark energy with a specific equation of state is real, can be calculated. Current observational constraints on W suggest that if the Big Rip occurs at all, it is at least tens of billions of years in the future, probably much longer. For a value of W equal to -1.5, a figure that is not ruled out by current observations, the Big Rip would occur approximately 22 billion years from now, roughly 8 billion years from the present. In the final billion years before the Rip, the Milky Way and Andromeda, which will have already merged by then into a single large elliptical galaxy, would be torn apart as the expansion overwhelms the galactic gravitational binding energy. In the final million years, the solar system would be disrupted, the sun receding from the Earth faster than gravity can maintain their bond. In the final months, the Earth itself would be ripped apart as dark energy overcame the self-gravity holding it together. In the final minutes, atoms would be ionized as dark energy overwhelmed the electromagnetic force. In the final microseconds, atomic nuclei would dissolve as dark energy overcame the strong nuclear force. The universe would end not in equilibrium, but in a state of total fragmentation. Matter dissolved to its constituent particles, expansion diverging to infinity in finite time. The Big Rip is cosmologically clean in one sense. It ends everything simultaneously, leaving no remnants to undergo the geological timescales of Hawking evaporation. But current observations slightly favor W being close to -1, consistent with a cosmological constant. The strongest observational constraints from the Planck satellite combined with supernova surveys and baryon acoustic oscillation measurements place W within a few percent of -1. Not phantom, not Big Rip territory, but not proven stable either. The Euclid mission and the Vera Rubin Observatory's legacy survey of space and time will constrain W to unprecedented precision over the coming decade. If they find W consistent with -1 to within 0.1%, the cosmological constant scenario is strongly supported, and the Big Rip becomes a less plausible fate. If they find a statistically significant deviation below -1, the implications cascade immediately into every model of the long-term future of the universe, vacuum decay, and the deepest possible instability. The standard model of particle physics describes the Higgs field, a quantum field that permeates all of space and whose non-zero value gives mass to the W and Z bosons, and through them, indirectly, to most other fundamental particles. The Higgs boson, discovered at the Large Hadron Collider at CERN in 2012, is the particle associated with excitations of this field, and its measured mass of approximately 125 gigaelectronvolts carries within it an extraordinary implication. The Higgs field exists in a particular vacuum state, meaning a particular value at every point in space that represents the lowest energy configuration of the field. But quantum field theory allows for the possibility that this is not the absolute lowest possible energy state. The Higgs potential, the mathematical function that determines how the field's energy varies with its value, could in principle have a deeper minimum at some different value, a true ground state lower in energy than the current state. If the current state is not the true ground state, it is called a false vacuum. It is stable enough for ordinary purposes, but not absolutely stable. Given sufficient time or sufficient energy, a quantum tunneling event could nucleate a bubble of true vacuum, a small region of space that transitions to the lower energy state. Measurements of the Higgs boson mass combined with measurements of the top quark mass, which enters critically into the calculation of the Higgs potential shape, suggest that our universe's vacuum state is either metastable or sits very close to the boundary between stability and metastability. The calculation is technically demanding and depends on precise values of parameters that carry experimental uncertainties, but the current best estimates place the universe in a condition of either metastability or marginal stability. Not clearly safe, not clearly doomed, sitting near the edge. If the vacuum is metastable, the implications are both specific and absolute. Somewhere, at some random location in space, a quantum tunneling event will eventually nucleate a bubble of true vacuum. This will happen at some point, with an expected rate per unit volume per unit time that can, in principle, be calculated from the shape of the Higgs potential. Inside that bubble, the laws of physics are different. The Higgs field has a different value, which means the masses of particles are different, which means the structure of atoms and nuclei and everything built from them is different, which likely means the physics inside the bubble is incompatible with the existence of anything recognizable as matter in its current form. The bubble expands at the speed of light. There is no warning. There is no signal that could precede it. Because the bubble wall moves at the maximum speed, information can travel. Any observer in its path would experience nothing. The laws of physics would simply change at the moment the bubble wall passed through them. Everything on this side of the wall, every atom, every structure, every thermodynamic process would cease to function in the way it currently does within the bubble the instant the wall arrives. This is not the gradual fading of heat death. This is not the slow dispersal of matter over googles of years. This is instant termination with no mechanism for survival and no process by which any currently existing structure could anticipate or respond to it. The universe, if vacuum decay occurs, does not end with entropy reaching maximum. It ends with the rules of physics changing faster than anything can respond. The probability per unit volume per unit time for vacuum decay, if the vacuum is indeed metastable, is calculated to be extraordinarily small based on current measurements. So small that the expected time before decay occurs within the observable universe is vastly longer than even the Hawking evaporation timescale of the largest black holes. The universe will almost certainly reach heat death long before vacuum decay occurs. But the probability is not zero, and in a universe without a defined endpoint, a non-zero probability is eventually a certainty. This is why cosmologists who think carefully about the long-term future of the universe treat vacuum stability as a genuinely open question rather than a reassuring footnote. There is a practical reason this matters beyond the philosophical exercise of contemplating the universe's ultimate fate. Though stability of the electroweak vacuum depends on physics at energies above what current accelerators can probe. Future measurements of the top quark mass and the Higgs boson mass at greater precision will sharpen the calculation of the vacuum stability parameter. A more precise determination of where the universe sits in the stability diagram, safely stable, marginally stable, or metastable, would tell us something fundamental about whether the current laws of physics are permanent features of reality or contingent accidents waiting to be superseded. Boltzmann, brains, and the quantum weirdness of infinite time. In the late 19th century, the physicist Ludwig Boltzmann was wrestling with a deep problem. The second law of thermodynamics says entropy always increases, but the microscopic laws of physics are time reversible. A collection of particles following the laws of classical or quantum mechanics does not intrinsically prefer one direction of time over another. The fact that entropy increases is a statistical consequence of the overwhelming majority of states being high-entropy states. If you start from a low-entropy state, almost every possible evolution leads to higher entropy. The second law is overwhelmingly probable, not absolutely certain. This creates a strange possibility. In a universe that exists for infinite or sufficiently long time, even at maximum entropy, random thermal fluctuations will occasionally produce localized decreases in entropy. Most of the time, these fluctuations are tiny, a handful of particles briefly correlated in a way slightly more ordered than the thermal average. But given infinite time, fluctuations of arbitrary scale and improbability will occur, including, in principle, fluctuations that produce structures of arbitrary complexity. Boltzmann himself considered whether the observable universe might be the result of such a fluctuation, a temporary local decrease in entropy in an otherwise equilibrium cosmos. He quickly recognized the problem with this idea. If the observable universe were a thermal fluctuation, it would be far more probable for a smaller fluctuation to produce only the minimum required for an observer to exist, rather than the vast, ordered cosmos we actually see. A fluctuation just large enough to produce a single brain, spontaneously assembled from the thermal background, with false memories of a universe it never actually experienced, would be enormously more probable than a fluctuation producing an entire galaxy-filled cosmos. This hypothetical entity is now called a Boltzmann brain. The Boltzmann brain problem is not merely a philosophical curiosity. It has become a genuine constraint on cosmological models. Any theory of the universe's ultimate fate that predicts an infinite future existence in a state of near maximum entropy, combined with the standard quantum mechanical interpretation that all sufficiently improbable but non-zero probability events occur, given infinite time, must confront the fact that it predicts an infinite number of Boltzmann brains coming into existence through thermal fluctuations. These fluctuating observers would vastly outnumber any observers who came into existence through the ordinary cosmic process of star formation and biological evolution. If Boltzmann brains dominate the population of observers in the universe's history, then any given observer is overwhelmingly likely to be a Boltzmann brain rather than an ordinary evolved intelligence. But a Boltzmann brain would have random, unreliable memories and perceptions, unable to trust its own observations. This leads to the self-undermining conclusion that if Boltzmann brains dominate, no observer, including any cosmologist reasoning about Boltzmann brains, can trust their own reasoning, the theory consuming itself. Some physicists argue that this is a serious enough problem to rule out certain cosmological models. A universe with an infinite future at near maximum entropy, combined with standard quantum mechanics, is arguably inconsistent. It predicts observers who cannot trust their observations. This has motivated proposals for mechanisms that would actually end the universe in a finite time, preventing the infinite accumulation of Boltzmann brains. The Big Rip, in which accelerating dark energy eventually tears apart every structure, including atoms themselves, would end the universe in approximately 22 billion years under some dark energy models and prevent the Boltzmann brain problem entirely by ensuring the universe does not persist long enough for appreciable fluctuation to occur. Other proposed endings involve the instability of the quantum vacuum, a mechanism worth examining closely because it has direct implications for whether anything in the universe can be considered genuinely stable. The black hole era ends, and the long wait begins. The end of the black hole era, roughly 10 to the power of 100 years from now, leaves the universe in a state that is physically simple and cosmologically profound in equal measure. All of the organized structures built over 13.8 billion years of cosmic history have been dismantled, stars burned out, galaxies dispersed by the expansion of space, white dwarfs cooled or decayed, neutron stars dissolved if proton decay occurred, black holes evaporated in their final bursts. What remains is an extremely dilute gas of the lightest stable particles, photons, neutrinos, electrons, and positrons, at temperatures barely distinguishable from absolute zero, spread across a space that has been expanding for a time so long that writing its age in years would require a number whose digit count exceeds the current number of atoms in the observable universe. The photons produced by Hawking radiation, and, if it occurs, by proton decay, will redshift continuously as the universe expands. Their wavelengths stretch, their energies diminish. They cool toward zero without ever arriving. The electrons and positrons, the lightest charged particles, might eventually find each other and annihilate, producing photons that themselves continue to redshift. The neutrinos, which interact so weakly with everything else that they have essentially been free since 1 second after the Big Bang, drift through the universe, encountering nothing. This is the state that physicists call maximum entropy, the heat death that Kelvin and Clausius first speculated about in the 19th century. Not a violent ending, not a dramatic collapse. An asymptotic approach to a condition so featureless and so uniform that in a precise thermodynamic sense, nothing can happen. Temperature differences drive physical processes. With no temperature difference anywhere in the universe, with energy spread as uniformly as the laws of physics allow, the arrow of time loses its direction. There is no thermodynamic future different from the thermodynamic present. The universe reaches a state in which the concept of change becomes undefined, not because nothing exists, but because nothing varies. And this is where the standard account of cosmic eschatology, the study of the universe's ultimate fate, usually stops. Heat death is the end. Physics has nothing more to add. The universe dissolves into featureless equilibrium, and the story of everything ends with a long silence. But there is more, and the more is strange: proton decay and the dissolution of matter itself. There is a layer of this story that depends on physics not yet confirmed but strongly theorized. The eventual fate of the matter in the universe, not just its organization into stars and galaxies, but the matter itself, the protons and neutrons in the nuclei of atoms, depends on whether the proton is stable forever or decays with a very long but finite lifetime. In the standard model of particle physics, as currently formulated, the proton is stable. A conservation law called baryon number conservation forbids it from decaying into lighter particles. The proton is the lightest baryon, the lightest particle carrying baryon number, and since baryon number is conserved, nothing lighter that it could decay into exists. Proton decay has never been observed. Experiments like Super Kamiokande in Japan, a tank containing 50,000 tons of ultra-pure water, surrounded by photomultiplier tubes waiting for a flash of light from a decaying proton, have placed extremely strong lower bounds on the proton lifetime. If the proton decays, it does so with a lifetime greater than approximately 10 to the power of 34 years for the most commonly predicted decay modes, but many theoretical frameworks beyond the standard model, particularly grand unified theories that attempt to unite the electromagnetic, weak nuclear, and strong nuclear forces into a single unified force at very high energies, predict that proton decay does occur, just with a rate so slow it has not yet been detected. In these frameworks, baryon number is not absolutely conserved. It can be violated by processes mediated by very heavy particles, whose effects become negligible at ordinary energies, but are not zero. The predicted proton lifetime in the simplest grand unified theories was around 10 to the power of 31 years, already ruled out by experiment. More sophisticated versions predict lifetimes up to around 10 to the power of 36 years, still potentially detectable by next-generation experiments. If proton decay occurs with a lifetime even near the upper range of current constraints, around 10 to the power of 36 years, the implications for the long-term future of matter are total. Every proton in the universe will eventually decay. The atomic nuclei that compose everything from interstellar gas to the remnant white dwarfs of the degenerate era will dissolve one nucleus at a time into lighter particles, primarily positrons and pions, which subsequently decay into photons and neutrinos. Over timescales around 10 to the power of 40 years, assuming proton decay occurs, all ordinary baryonic matter in the universe will have converted to radiation. White dwarfs and neutron stars, the stable remnants that were going to cool and persist indefinitely in a universe without Hawking radiation, will instead erode from within as their constituent protons decay, converting from dense degenerate matter to diffuse clouds of radiation over timescales shorter than the Hawking evaporation time of even stellar mass black holes. The two processes, proton decay and Hawking evaporation, are not alternatives. They operate on different objects. Proton decay destroys ordinary matter. Hawking evaporation destroys black holes, which are not made of protons in any conventional sense. If proton decay occurs, matter is gone long before the black holes finish evaporating. What remains after proton decay is complete is a universe of black holes, photons, and the lightest stable leptons, primarily electrons and positrons, drifting at enormous separations through space, still expanding under dark energy. Then, the black holes evaporate one by one across their own enormous timescales. And eventually, as the last supermassive black hole releases its final Hawking burst, the universe enters its final epoch, Hawking radiation and the evaporation of everything. In 1974, Stephen Hawking combined quantum mechanics and general relativity in a calculation that produced a result nobody had expected. Black holes are not perfectly black. They radiate, slowly at a temperature that for stellar mass black holes is vastly colder than the cosmic microwave background and essentially undetectable by any current instrument, but continuously and inexorably. And the implication of this radiation is that over a long enough time, every black hole in the universe will evaporate completely. The mechanism involves the quantum vacuum and the properties of the event horizon. Quantum field theory requires that empty space be filled with virtual particle pairs, particle and antiparticle partners that spontaneously appear together, briefly exist, and then annihilate back into the vacuum. This is not merely theoretical. The Casimir effect, the measurable attractive force between two uncharged metal plates in a vacuum, is direct experimental confirmation that the quantum vacuum has energy and structure. Virtual particles are as real as the physics that predicts them. Near the event horizon of a black hole, something unusual can happen to these virtual pairs. One member of the pair can fall inside the horizon, while the other escapes before annihilation can occur. The escaping particle becomes real, carrying energy that ultimately comes from the gravitational field of the black hole itself. The black hole loses a tiny amount of mass with each such event. Summed over the event horizon area, this produces a thermal spectrum of radiation at a specific temperature inversely proportional to the black hole's mass. Larger black holes are colder. Smaller black holes are hotter. For a stellar mass black hole of a few solar masses, the Hawking temperature is roughly 60 nanokelvins, 60 billionths of a degree above absolute zero. The current temperature of the cosmic microwave background is 2.725 Kelvin, vastly higher. A stellar mass black hole is not currently evaporating in any net sense. It is absorbing far more radiation from its environment than it emits. Only when the universe has cooled sufficiently for the background temperature to drop below the black hole's Hawking temperature will net evaporation begin. For the universe's most massive black holes, in the range of tens of billions of solar masses, the Hawking temperature is below a femtokelvin, 10 to the power of -15 Kelvin. The universe will need to cool enormously before evaporation dominates for them, but the expansion of space is continuously cooling the cosmic background, stretching photon wavelengths and draining them of energy. Eventually, the background will cool below any black hole's Hawking temperature, however low. And then, evaporation takes over. The evaporation timescale scales with the cube of the black hole's mass. Double the mass, and the evaporation time increases by a factor of 8. A stellar mass black hole of 2 solar masses will evaporate in roughly 10 to the power of 67 years. A supermassive black hole of 10 billion solar masses will require approximately 10 to the power of 100 years. Both of these numbers are so large, they require scientific notation to be legible. Written in full, 10 to the power of 100 is a 1 followed by 100 zeros. A Google, the number whose name inspired the company. No physical intuition scales to these numbers. You can only acknowledge them and move forward. The process of Hawking evaporation accelerates as the black hole shrinks. As mass decreases, the Hawking temperature rises. Higher temperature means faster radiation. Faster radiation means faster mass loss. The feedback is self-reinforcing. The final fraction of a second of a black hole's evaporation is a burst of high-energy radiation, as the remaining mass converts almost entirely to photons and lighter particles. The black hole does not simply disappear quietly. It ends in a flash, brief and final, the last gasp of something that persisted for timescales incomprehensible to anything that might observe it. After the last black hole evaporates, the universe will consist of the decay products of Hawking radiation, mostly photons, and the lightest particles that quantum mechanics allows to be stable, along with any long-lived particles that the Standard Model permits. There will be no stars, no planets, no remnants of galaxies. The matter that built everything from the first stars to the last complex molecules will have been converted to radiation, drifting through a space still expanding under the influence of dark energy. The universe will be almost perfectly empty, almost perfectly uniform, and still cooling toward absolute zero. Almost the degenerate era and what fills the darkness. After the last star burns out, the universe will not be empty. It will be filled with the corpses of stars, objects that carry the mass and structure of their predecessors without the energy output. White dwarfs, neutron stars, and black holes will inherit the universe. And in the darkness of the degenerate era, roughly 10 to the power of 15 years to 10 to the power of 40 years from now, these remnants will define the physics of everything that remains. White dwarfs are the most numerous stellar remnants. They form when stars between roughly 8/10 of the Sun's mass and about 8 times the Sun's mass reach the end of their lives. The outer layers are expelled as a planetary nebula, and the remaining core, primarily carbon and oxygen, collapses under gravity until it reaches a density where a quantum mechanical effect called electron degeneracy pressure halts the contraction. The Pauli exclusion principle, which forbids 2 electrons from occupying identical quantum states, creates an effective pressure that has nothing to do with temperature. A white dwarf does not need to be hot to support itself. It just needs to be compact enough that electron degeneracy provides the necessary outward force against gravity. This means that white dwarfs cool over time, without collapsing. They radiate away their thermal energy across timescales far longer than the current age of the universe. A white dwarf formed today from a star like the Sun will still be cooling 50 billion years from now. Eventually, after roughly 10 to the power of 15 years, the most massive white dwarfs will have cooled to temperatures indistinguishable from the ambient temperature of the universe. They become what theorists call black dwarfs, objects with the mass and size of white dwarfs, but no thermal luminosity, invisible against the black sky, because they radiate no more energy than they receive from the vanishingly thin background around them. There is an important caveat here that is worth stating explicitly. No black dwarf currently exists anywhere in the observable universe. The universe is not yet old enough. Not a single white dwarf formed since the Big Bang has had sufficient time to cool to the black dwarf state. Every white dwarf in the cosmos is still warm, still glowing faintly. Black dwarfs are a theoretical prediction about what those same objects will become in a future so remote that our current era of the universe is not even a visible fraction of the time involved. When cosmologists talk about black dwarfs, they are talking about physics that is correct and unavoidable, but that has not yet been instantiated anywhere in existence. Alongside the cooling white dwarfs, neutron stars will persist in the degenerate era. These form when stars between roughly 8 and 20 times the Sun's mass exhaust their nuclear fuel and collapse in a core collapse supernova. The protons and electrons of the collapsing core are forced together by the extreme pressure to form neutrons through a process called inverse beta decay. And the result is a sphere roughly 20 kilometers across, but containing 1.4 to 2 times the mass of the Sun. Neutron stars are supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect analogous to electron degeneracy in white dwarfs, but operating at far higher densities. The material in a neutron star is so compressed neutron stars in the degenerate era will be cold, dark, and slowly spinning down as their rotational energy is lost to electromagnetic and gravitational radiation. They will be harder to detect than even black dwarfs because they are smaller and have even less thermal surface area. The universe of the degenerate era will be populated by these invisible remnants, separated by distances that have grown enormous as the expansion of space continues to push everything apart, drifting through a darkness that has no active sources of light. And then there are the black holes. The degenerate era will contain black holes ranging from stellar mass, a few times the Sun's mass, up to the supermassive black holes at the centers of galaxies, which range from millions to tens of billions of solar masses. These objects are in one important sense permanent. Nothing in the standard model of physics allows matter that has fallen inside a black hole's event horizon to escape. Black holes grow by absorbing matter. They do not spontaneously shrink. They seem to represent an asymptotic endpoint, a one-way destination for matter and energy. But they are not permanent in the strict sense. Hawking radiation changes everything, and the era after the black dwarfs will be defined entirely by it, the stelliferous era and its limits. We live at a cosmologically unusual moment. Not special in any anthropic or privileged sense, but unusual in the sense of being statistically brief. The universe in its current form, full of burning stars, radiating galaxies, and the complex chemistry that makes life possible, is a transient condition. It will not persist. The ingredients that make it possible are being consumed, and the stockpiles cannot be replenished. Every star in the sky is a controlled thermonuclear reaction, fusing lighter elements into heavier ones and releasing energy in the process. The Sun fuses approximately 600 million tons of hydrogen into helium every second. That sounds inexhaustible. It is not. The Sun contains enough hydrogen to sustain this fusion for a total of roughly 10 billion years, of which about 4.6 billion have already elapsed. In approximately 5 billion years, its hydrogen supply in the core will be depleted. The Sun will expand into a red giant, eventually shedding its outer layers and collapsing into a white dwarf, a dense, hot remnant that will cool over trillions of years without generating any new energy. The Sun is not unusual in this respect. Every star in the observable universe is doing the same thing, converting hydrogen to helium, helium to carbon, carbon to heavier elements in the more massive cases, and in doing so, spending down the finite reserves of fusible material that existed when the star formed. The universe began with almost pure hydrogen and helium. Stars convert hydrogen to helium and helium to heavier elements. Those heavier elements are partly expelled when stars die, enriching the gas clouds from which the next generation of stars form. But each generation leaves behind a higher fraction of material that cannot be fused for further energy gain. Iron, the endpoint of stellar nucleosynthesis, cannot yield energy through fusion or fission in most conditions. It is the thermodynamic dead end of nuclear burning. Stars that accumulate iron cores collapse rather than fuse further. The total amount of fusible hydrogen in the observable universe is finite, and it is decreasing. New stars are forming from gas clouds today, but the rate of star formation has been declining for roughly 10 billion years. It peaked around 3 billion years after the Big Bang, when the universe was densest and gas most abundant. Since then, galaxies have been converting their gas into stars faster than stellar deaths return it in fusible form. The universe is running out of the raw material for starlight. Current estimates suggest that the stelliferous era, the cosmological epoch defined by the presence of main sequence stars actively fusing hydrogen, will last from now until roughly 100 trillion years from today. That number, 10 to the power of 14 years, represents a period roughly 10,000 times longer than the current age of the universe. To a human perspective, it is incomprehensible. To cosmological timekeeping, it is a brief prologue. The vast majority of cosmic time lies on the other side of it. The last stars to burn will not be dramatic. They will be the smallest, the dimmest, the most miserly with their fuel. Red dwarf stars with masses between about 8% and 40% of the sun's mass burn so slowly and so completely that they will persist long after every sun-like star has burned out. The least massive red dwarfs currently known will sustain fusion for somewhere between 1 and 10 trillion years. They are inefficient in their luminosity, but extraordinarily efficient in their longevity. When the last of them finally exhausts its hydrogen, there will be no new stars to replace it. The stelliferous era will have ended, and the universe will enter a darkness from which, under standard physics, it will not recover. Before we can talk about how the universe ends, we need to be precise about what ending means when applied to something that contains everything. The universe will not end the way a fire ends, consuming its fuel and going dark in a moment you could watch. It will not end the way a star ends, in a flash of energy followed by a quiet, cooling remnant. It will end the way complexity ends, gradually, across timescales so enormous that the entire current age of the cosmos will look in retrospect like the opening sentence of a very long book, most of whose pages describe nothing happening at all. The second law of thermodynamics is the engine driving all of this. It states that in any closed system, entropy increases over time. Entropy is a measure of disorder, of the number of possible arrangements a system's components could occupy. A hot cup of coffee, sitting in a cool room, will always transfer its heat to the surrounding air. The heat will never spontaneously flow back into the cup. The ordered state, heat concentrated in the coffee, converts to the disordered state, heat diffuse throughout the room, and not the reverse. This happens not because of any force specifically directed at disorder, but because disordered states are statistically overwhelming. There are vastly more ways for energy to be spread evenly than to be concentrated, and random processes find the common outcome far more often than the rare one. Apply this to the entire universe, and the endpoint is called heat death. Not heat in the sense of high temperature, heat in the thermodynamic sense, energy in its most diffuse possible state, spread uniformly across all of space, incapable of doing work because work requires a difference in temperature between two regions, and heat. Death is defined precisely by the absence of any such difference. The universe at heat death is not hot. It is cold beyond anything currently existing. A vanishingly thin background of radiation, and the occasional particle drifting through a darkness so complete that no process anywhere can generate a photon of visible light. This is the final state that physics predicts for a universe like ours, not tomorrow, not in a billion years, but eventually, on timescales that make the age of the universe look like a rounding error. What makes this worth taking seriously is not that it is dramatic. It is the opposite of dramatic. What makes it worth taking seriously is that it is demanded by the most rigorously tested law in all of physics. The second law of thermodynamics has never been observed to fail. Not once, not at any scale, not under any conditions. Every process in the history of the observable universe has abated, and what it says, applied with patience, is that complexity is temporary and equilibrium is forever. But the path to that equilibrium is not simple or uniform. It passes through stages, each with its own character, each separated from the previous by timescales that require a new way of thinking about numbers. To travel through those stages properly, we need to start where we are, in what cosmologists sometimes call the stelliferous era, the age of stars, and trace what happens when that age ends. The universe is older than almost anything in it. Every atom in your body has existed in some form since the first few minutes after the Big Bang, forged from the primordial plasma that filled all of space when the cosmos was smaller than a single galaxy. You are not visiting the universe, you are made of it. And for 13.8 billion years, all of that matter has been doing something relentless and strange. It has been cooling, spreading, thinning, organizing briefly into complexity, and then surrendering that complexity to entropy. The stars are burning through their fuel. The galaxies are pulling apart. The thermodynamic clocks of everything that exists are running in one direction and cannot be rewound. Tonight, we trace that direction to its end, not to a wall or a boundary or a place called finish, to a set of conditions so alien that time itself may cease to have a direction. Subscribe if you are new here. Settle in, because the far future of the universe is stranger than almost anyone expects, and the path to it is written in physics that has already been confirmed. Part 1. What it means for the universe to die.